Hello everyone and welcome to The Wild Side. This is your host Kight, and that was Bonnie Raitt with The Fundamental Things. And on this week's show I want to continue in the vein that I've been going in for the last couple of shows, and that's to kind of think about things in the realm of chemistry and especially physics. So this all started off a couple of weeks ago when I was talking about tin, and I had been interested in that topic and in elements in general and the periodic table, because I was reading a book about the history of the periodic table and the ways in which the elements have contributed to kind of our society and our culture. Well, that kind of got me interested in some specific researchers, scientific researchers that I had read about in that book. So last week I talked about Berzelius and also Lise Meitner. And I followed that up by beginning to read Lise Meitner's biography, kind of the definitive biography, which is really interesting because it talks about her personal life, and she was a fascinating person. But also it's been a little bit frustrating because there is quite a lot of discussion in the book about the physics and chemistry research that she did throughout her career. And the author of the book is kind of an expert in chemistry and has written a lot about the history of chemistry, and so she throws around a lot of terms that I haven't really thought about since I was in high school. And certainly there are some very advanced concepts as well that I never really learned about at any point. So finally I got frustrated and I got online and started reading about the atom and kind of the fundamental components of the atom and the way that these things fit together and the way that they interact with each other as well. And this, of course, is really the realm of Meitner's research, thinking about chemicals that are decaying and elements that interact with each other and forming compounds or splitting apart, and ultimately the discovery of the process of nuclear fission. So all this was really helpful for me, and actually I thought that it would be interesting to kind of try to work through these concepts a little bit on today's show, because maybe some of you out there are also as ignorant of physics and some basic chemistry as I was, and actually as I still am. I'm sure that there are some things in here that I'm maybe not explaining in the best of ways because I still don't fully understand them. So this is kind of a journey in a way that I guess we can kind of take together. And what I'm hoping is that if I do make mistakes, you guys can write in and let me know, and I can fix them on the webpage so we can kind of learn from each other. So starting off with a brief history of not the atom itself, but the idea of the atom, because actually this is very much the realm of Lise Meitner's research. Kind of, she existed at this really, really fascinating time, what was considered the golden era of physics, when there were all sorts of discoveries being made that really advanced people much further from where they had been and into what we consider now the modern era of physics. And so it's really interesting to think about the history of the idea of the atom, because there were so many changes that happened at that time, and it was just so fundamentally different from what it had been in the past. So going back to the very distant past, the word atom comes from a Greek word, atomos, which indicates something that is indivisible. So it was a concept that was first proposed, even if that specific word wasn't used, by early Indian and Greek philosophers dating to the 5th and 6th centuries. And the word itself comes from Democritus, who coined it in 450 BC to reflect the philosophical views of his mentor Leucippus. So all of these people at this time thought that the atom was this thing, and of course they didn't really have a concept of it back then in terms of, what it looks like and maybe how it functions. But they did feel that there was a thing that was the fundamental unit of all other things in the universe. So you could split them apart, you can chop down a tree, you can cut it into firewood, you can burn it and have ash, but they knew that eventually you could keep going and you would come up with one final particulate bit at the end that you couldn't break down anymore. And that was what the concept of the atom was. And one of the first people to apply this concept as we now know it was Robert Boyle. And he wrote in a book called The Skeptical Chemist that matter was composed of discrete units rather than the 4 classical elements that we, before that time, had typically cited, so air, earth, fire, and water. So he was the first person who thought that rather than those things, it was this thing called an atom that would make up all the things we see in the universe. And it was the development of the field of chemistry that really helped clarify and identify the role of the atom. Now, I kind of mentioned earlier that Lisa Meitner and other researchers at that time did a lot of chemistry and physics, and that was because there was this period where there was considerable overlap in how you would study these two things. And actually even now, I mean, these concepts, of course, they fundamentally affect one another. But it's quite interesting that a lot of what we consider physics today was thought about and was first identified, certain properties and elements and things like that, by chemists. So in the 18th century, one of the big names was Lavoisier, and he realized that there were these basic substances that could reach chemical endpoints. And this is the phrase that he used. So it would get to a process, it would go through a process and get to a point where you could no longer have any further processes and break things down anymore. And then in the early 19th century, not too long after, John Dalton followed up on this by saying that each of these elements was actually a type, each of the elements that we know, was a type of chemical entity that was made up of a collection of similar atoms. So he recognized also that you could get to this kind of endpoint, and that you would have similar kind of groups of endpoints, and these things were the elements, and they were made up of these different similar atoms. And because of this observation, this is kind of getting the closest to what we know of today as the concept of the atom, and that's why he's considered to be the originator of the modern atomic theory. And it was clear at this point that atoms had to be quite small, but it wasn't until the early 20th century that they were actually measured. So someone named Loschmidt measured air molecules in 1865. And of course, molecules aren't single atoms, they are aggregates of atoms, but at that point, that was as small as they could get in terms of measuring these things. But then shortly thereafter, another researcher named Brown was able to use a microscope to observe the outcome of molecular motion. And this was, what he was seeing was the movement of pollen grains on water. And he saw that even though this water itself wasn't moving, there was no breeze, he could see that the pollen grains were moving around. And it turned out that the reason they were moving around was because of the thermal energy of the water itself. It was the molecules of water moving around and carrying the light pollen grains on top of them. So this is what we now call Brownian motion, and Einstein mathematically described this erratic motion using a series of equations in 1905. And this was really important because another scientist named Perrin was then able to use Einstein's mathematical logic to experimentally determine the mass and the dimension of atoms. So this meant for the first time, finally, after the turn of the 20th century, we were able to kind of get a grip on what an atom was, how big was it, and what was it doing in the real world. So this brings us into kind of another phase of existence, which is being able to measure and understand the atom in a real world sense. Now, in the late 19th century, researchers began to make a lot of different discoveries, kind of one right after the other, building on each other. And all of these things started to reveal that, contrary to what the name atom, the indivisible, suggests, actually atoms are made of smaller components. In 1897, for example, the scientist Thomson discovered that the electron is something that exists and is part of the whole concept of the atom. And this was the first proof that atoms are not indivisible entities, but are actually made up of these other components. So what are electrons? This is definitely a word that you've come across, but sometimes we don't really know what these things are, what actually they do in the real world. So electrons are negatively charged, and they have an extremely small mass. They're only a tiny portion of the whole mass of an atom. They can act like both particles and also waves, and that means that they can collide with other particles and interact with those other particles, and they can also be diffracted the way that light is, so they can bounce around and kind of be moved in their paths and go in opposite directions and new directions, and that makes them kind of, in a sense, volatile, and it makes them able to interact with lots of things. Now, electrons are essential to easily recognizable physical phenomena that we're all probably familiar with. So things like electricity, magnetism, thermal conductivity, it's electrons that allow these things to happen. And this means that they have many useful applications. We use them in electronics, in welding, in cathode ray tubes, which is what we find in televisions. We use them in microscopes and in lasers and all sorts of other tools, sometimes very modern tools. So they are really fundamental to the existence that we have today. Now this is when things start to get a little bit crazy, because physics is full of language, lots of terms that you have to come to grips with, and I definitely don't have all of this memorized. I have a cheat sheet in front of me. So electrons are a type of something called a lepton. And leptons are particles that have a very particular type of spin. And in this case, they have a spin of 1/2. And this reflects the angular momentum of a particle. So you can have a positive spin or a negative spin, and this indicates how much angular momentum you have. Now leptons can either be charged, as in the case of an electron, which as I said is negative, or they can be neutral. And the charged versions can combine with other particles to create composites, and this is what we find in the case of atoms, for example. But the neutral versions rarely interact with other entities, and therefore we rarely observe them. Now, there are 6 different flavors of leptons, and the heavier of these are produced by really high energy collisions. So, for example, when you've got cosmic rays or when you've got particle accelerators, obviously the first of those is more natural than the other, which is artificial, created by humans. And when they interact in this way, because of these collisions, they can decay into electrons. So these heavier ones decay into the lighter ones like electrons. And that means that you've often got a lot of electrons around. So you've either got electrons to begin with, or you've got these heavy things turning into the lighter things, electrons in this case. And that means electrons, in fact, are the most stable and also the most commonly found charged lepton in the universe. Now, in 1909, researchers went on to discover evidence of the atomic nucleus. So as I'll get into a little bit later, the electrons are kind of outside of the nucleus, and then the nucleus is right in the middle of the atom. And the people who are responsible for making this discovery are Geiger and Marsden, who are working under Rutherford. You've probably heard of Rutherford because he was British, working at Cambridge. He won a Nobel Prize. You've probably also heard of Geiger, who is responsible for the Geiger counter, which can detect radiation. So what these guys did was bombard sheets of gold foil with alpha rays, and alpha rays are positively charged helium atoms. And when they did this, they found that some of the particles were bouncing off in an unexpected manner. So they mostly expected the particles to go right through the gold foil, because the particles are quite fast, they're powerful, they expected them to penetrate right on through. But the fact that they were bouncing off indicated that there was something in there that had a heavier mass than those alpha rays had, and was therefore deflecting them and sending them off on another path. And Rutherford, these guys were working in his lab, and they brought these results to him, and he's the one responsible for interpreting this as being indicative of a nucleus, so something that's at the center of each of those atoms. So you would have lots of space around them, and that's where most of the alpha rays were going through, but then every now and then you'd have one hit this strong nucleus that's right in the center. And in addition to deciding that there was this thing within the atom, he also suggested that they possessed a good deal of positive charge because of the way that these things were reacting, the way that the alpha rays were bouncing off. Now, several years later, Niels Bohr came up with a model that most of us are familiar with today, and of course he was building on what Rutherford proposed. And what Niels Bohr thought was that electrons were probably confined into clearly defined orbits that surrounded the nucleus. So they're not just kind of hanging out and all over the place and kind of a mess. They actually had these defined areas that they were finding themselves in over and over again and sticking around in those areas. And he suggested that electrons might be able to jump between these orbits, but that they could only do so if they absorbed or emitted specific amounts of energy. And this energy is referred to as a photon. And a photon, and this is probably again a term that you've heard at some point, this is defined as a quantum of light or other forms of electromagnetic radiation that possesses both wave and particle qualities. And quantum is another word that probably needs definition in this case. You may have looked this up when the James Bond movie came out a few years ago, because everyone saw that title, Quantum of Solace, and wondered what on earth it meant. And so I certainly looked this up because I was trying to figure out if it actually made sense or if it was just, was chosen because it sounded fancy. Well, a quantum is the minimum amount of a physical entity that's involved in an interaction. So in this case, a photon is this minimum amount of light energy that you have to have that will move, that will interact with these other things that it's encountering. So in this case, it's the minimum amount that's required to move an electron into a different orbit. So gain of a photon, so having more energy than you had before, will move an electron into a higher orbit, and the higher orbits again are signaling more energy, and these are farther away from the nucleus. And again, if you kind of think about, it's a bit of a tenuous analogy, but if you think about the planets orbiting around the sun, you know that the farther out they are, the less maybe of a connection there's going to be between those planets and the pull of the sun. And so it might be a little bit easier for something to maybe hit those things and nudge them off of their orbit and out into deep space. Well, that's kind of a similar thing to what you've got going on here. When the electrons aren't quite as close to the nucleus, they're in that higher energy state, it is a bit easier for them to do something else other than just exist around that nucleus. On the other hand, if you've got an electron that loses a photon, so it loses a bit of energy, it will push it down into a lower orbit where it's closer to the nucleus and things are maybe a bit more stable. And all of this explanation provided by Niels Bohr allowed researchers to understand that chemical bonds were the result of interactions between the electrons of different atoms, and further, that those electrons were clustered in such a way as to facilitate those interactions. So this all prompted the idea of electron shells, and I mentioned this when I was talking about tin, because I said that tin was considered to have this kind of perfect magic nucleus, and that had to do with the arrangement of its electron shells. And what these are regular orbits that electrons are making around the atom's nucleus. And we label these either with numbers or with letters, so sometimes they're called shells 1, 2, and 3, and so on. Other times they're labeled with with letters, and they're known as K, L, M, P, and again, so on. Different shells can contain fixed numbers of electrons, and you can calculate this by using the formula 2n squared. So if n is the shell number, then the number of electrons you can find in that shell is 2 times that number squared. So this means you've got 2 in the first shell, 8 in the next one, 18 in the next one, and so on and so on. And it's the number of electrons in the outermost shell, which is also called the valence shell, that determines an atom's chemical properties. So with elements like tin, where you've got every single one of those shells completely full, that's why it's more stable and it's not interacting with as many things. But when you've got a valence shell that isn't quite as full, then that atom is going to be looking for things to either pluck away those stray electrons in order to empty that shell and then just have that next closest shell be the full one, be the outer one that's now full, or it's going to pick up electrons from elsewhere and try to complete that shell, and again, in order to make it more full and more stable. And sometimes it can actually yank electrons away from something else, other times it ends up just sharing those electrons, and so you've got compounds of atoms made. So it's all about kind of filling those shells or getting rid of excess things so that you can reduce down to a shell that is already full. And all of these patterns and understanding all of this help explain the usefulness of the periodic table. And again, I did talk about this a couple weeks ago with tin, because the periodic table arranges elements in such a way that the chemical properties are repeated in a predictable and a periodic way, hence the name. And so this explains this fact that you've got this kind of shared pattern of valence shell. This explains why all of those relationships are obvious at a glance when you're just looking at that periodic table. Welcome back to The Wild Side. This is your host, Caitlin Kight, and that was Ryan Adams with Nuclear. And on today's show, I am talking about the atom. And just before the break, I was talking about the electron and how the discovery of the electron helped people figure out how an atom is arranged, and how that understanding kind of explained why the periodic table is such a useful tool for predicting the behaviors and grouping elements together depending on how many electrons they have and kind of how interactive they are with the things around them. Now, after the discovery of the electron, probably I would say the most important thing that happened was that Moseley was able to perform some experiments that revealed that an atomic nucleus contains a number of positive charges, which goes back to what Rutherford was predicting after he saw those experiments of his students in his lab, and that also the number of positive charges is equal to the atomic number in the periodic table. And this was the first time that the atomic number had been shown to indicate both a physical quality and also an experimental quality. So it had moved beyond the realm of this kind of theoretically useful thing into something that actually meant something in the real world. And these positive charges are what we now know are protons, which are subatomic particles that were actually first proposed back in 1815, but they weren't discovered until about 100 years later by Rutherford. Now, each atom has at least one proton, and the number is unique for each atom, and this is why we can use this as an atomic number that helps us arrange all of these things in the periodic table. Protons are, again, I'm going to get into the terminology here, and it gets totally crazy from here on out. Protons are a type of fermion, and a fermion is a particle that is characterized by certain statistics, the Fermi-Dirac statistics. And you don't really have to know much about that. It's just to say that there are different types of particles that are kind of governed by different mathematical formulations, and so that's how they get these names. And in this case, it was Fermi and Dirac who came up with the statistics that help describe fermions. And there are lots of different things that kind of fall into this category. So this includes quarks, leptons, baryons, also some atoms and some nuclei as well. In fact, many atoms and nuclei also fall into this category. Now, protons are composed, we now know, of three smaller units known as quarks. For a really long time, people thought that protons might have been also a fundamental body, just the way that we used to think that atoms were a fundamental body. But again, just as we discovered that atoms actually have multiple bits and pieces, we discovered the same thing about protons. Now, quarks are never directly seen or found in isolation, but they're always found within composites known as hadrons. So if you've heard of the Hadron Collider, now you know why that term is used. So quarks can have an up charge or a down charge. So basically an up charge means that these are positive, and a down charge means that they are negative. So protons have two up quarks and a down quark, whereas there are other things that have two down quarks and an up quark. Sorry, I know I'm probably blowing your mind with all this, but I am almost done with the crazy terminology in this little section. So the hadrons fall into one of two classes, and this is the last couple phrases I'll introduce for now. The first is baryons, and baryons are made of three different quarks, so again, things like protons and neutrons. And then there are also mesons, and these are made up of a quark and an antiquark. So just to recap all of that, baryons are a type of hadron, and hadrons are a collection of quarks. One type of hadron is the proton, and that itself is a type of fermion because of the statistics that can be used to describe it. And of course, I think the average person would never be expected to memorize all of this and to use this in any real way. It's just kind of fun to mention all of these things and think about the fact that there are people who exist in this world who kind of use these thoughts and these concepts on a regular basis and remember all of this stuff. And I just find that absolutely incredible that all of these different ideas exist. So now, what does all this mean? Well, in other words, the overlap of all these classifications reflects the fact that some terms indicate physical makeup, others indicate behaviors and the mathematics that are used to describe those behaviors, and so you use these different phrases at different times depending on what idea you're really trying to get at. So unlike leptons, so things like electrons, baryons participate in the strong interaction. And this is important because it's one of the four fundamental interactions that physicists have described in nature. Others include electromagnetism, the weak interaction, and also gravitation. So why is the strong interaction even important? Well, this is the thing that helps hold these things together in the atomic nucleus. Three quarks are held together by little particles called gluons, and these are exchange particles that facilitate the effect of the strong force on the quarks. And that is as far into detail as I'll get on that concept, because really my mind just cannot cope with this idea. But basically the gluon works to, just as its name suggests, it kind of glues these particles together by allowing the strong interaction to make these quarks stick around into the shape of things like protons, which is, again, crazy. So another phrase that's also associated with protons is nucleons, and that just indicates the fact that these particles are found within atomic nuclei, where they're bound together by the nuclear force. Of course, the other nucleon is the neutron, which I've mentioned already a couple of times, but not really gone into much detail about. So the neutron is a neutrally charged hadron, specifically a baryon. So you remember I was discussing all those different categories. And it was not discovered until 1932. People kind of knew that there was something that was likely to be in there, but they didn't actually have evidence of it until 1932. Now, unlike protons, which are another type of baryon, neutrons are they're made up of one quark that's up and two quarks that are down. So remember I mentioned there was something that was kind of opposite to the proton. Well, that's what the neutron is. So that's why these two things have differences in mass and charge, despite the fact that they're both made up of the same number and kind of, in many ways, the same types of constituent units. So just the orientation of those quarks, the physical charge of the quarks, makes a real difference in terms of how these things end up behaving. And neutrons and protons do have very similar masses. They're almost equal, but not quite, and that is because of the difference of whether they've got two ups and one down, or two downs and one up. Now these guys all bind to each other and also to proteins, to protons, via the nuclear force, and that helps provide a lot of stability in the nucleus. And cumulatively, it's the protons and neutrons together that are responsible for the mass of the nucleus, and in fact, the mass of most of the atom, because as I said, the electrons are incredibly, incredibly light, and so really, when you've got something rounded to, maybe 2 or 3 different decimal places, as you tend to see it in the periodic table, that doesn't really reflect what the electron weighs, because it's something like 1/1800th of everything else. So it's really these two different components that are making up most of the mass of the atom, and indeed, as I said, of the nucleus itself. So this discovery of the neutron finally helped explain the concept of isotopes. And isotopes had been proposed at the turn of the 20th century. And actually, a female scientist, coincidentally, played quite a big role in this, which is quite nice. The whole reason I got interested in Lisa Meitner and this kind of chemistry and physics history was because I did think it was remarkable that she was a woman working in this field when so many other women were also doing it. But in fact, a lot of these women that actually stuck it out and played this game when there were tons of men around, they were up for the battle. They actually made some really significant contributions, and it is a female that was one of the people who came up with the whole idea of what an isotope was. And this happened at the turn of the 20th century, and we now know that isotopes are versions of an element that have the same number of protons but different numbers of neutrons. And I've talked about this a little bit in the past on the show, and I've talked about how you can age something using these different isotopes, and also how you can figure out where something came from by looking at the different isotopes that you might find, for example, in its feathers or in a blood sample. So because you tend to find different isotopes at different ratios in different places, that's why we're able to do these analyses. So these things that we see in the world of chemistry and physics do actually have some application in the rest of the scientific world as well. So again, just to have another little recap of all these things, by 1932, physicists and chemists had identified all the major bits and pieces that we now know make up the atom. And this led to an understanding of the atom that we have today. So basically that it's the fundamental unit of matter, in which there's a dense central nucleus that's made up of positively charged protons and neutrally charged neutrons. And all of this is surrounded by a cloud of negatively charged electrons that are responsible for interacting with, or not, as the case may be, other elements in the world around them. Welcome back to The Wild Side. This is your host, Kight, and that was Marina and the Diamonds with Radioactive. And on today's show, I'm carrying on in my theme of physics and people related to physics by thinking a little bit about the atom, what the atom is and what it does. And just in case you're just now joining me, I'll reiterate that the whole reason I got interested in this was because I've been reading a couple of really interesting books. And I have been updating the website as I've gone along. So if you're interested in pursuing some of these books for yourself, you can find out more about them on the Wild Side website on, again, the Source FM page. And you can also find out about some of the other stuff that I've talked about. I'm posting links and also some images to help make all these concepts a bit clearer. So just before the break, I was talking about kind of the anatomy of the atom, if you like. And now I want to think a little bit more about the activities of the atom. And one of the reasons that this is so interesting to me is that this biography that I've been reading about Lise Meitner, it discusses not just these entities, things like neutrons and protons and electrons and all these little particles that have been I've been discussing as part of the atom, but also what they do. And because this is the research that Lise Meitner was conducting. She was interested in looking at how these little particles interact with the world around them and how this explains certain reactions that we see. She was particularly interested early on in radioactivity, and later she began to be interested in nuclear fusion and nuclear fission in particular. So these are the two things that I really want to focus on now. And the reason that we see both of these processes is that it is possible to change the number of protons and neutrons in an atomic nucleus. And this generally requires really high energies. And these are what we see when we've got nuclear fusion and nuclear fission processes. So first of all, to start with nuclear fusion, this is when you've got two or more atomic nuclei that collide at really high speeds, and they, at the end of that, create a new type of atomic nucleus. And when this happens, some of the mass from the nuclei is converted into photons. And I mentioned earlier that photons are this quantum, this minimal quantity of light or other forces. And when the fusing nuclei have masses that are lower than that of iron, the fusion process generally releases energy. It's referred to as being exothermic. If the mass of the nucleus produced by the fusion reaction is less than the sum of the masses of the particles that existed prior to the reaction, then the difference between those two measurements is the exact amount that's going to be released as that exothermic reaction product. And basically this is kind of a potentially usable energy that can be sucked up by something afterwards and used as a result of that fusion event. And this is what's described in the mass energy equivalence formula that was produced by Albert Einstein. So his formula, of course, we all know, E equals mc squared. And what that means is energy equals mass loss times the speed of light squared. And the difference is known as the binding energy of the new nucleus. And this energy is non-recoverable, and it's the same amount of energy that would be required if you wanted to then re-separate those two fused nuclei that came together in the fusion interaction. And we see this a lot in stars. So nuclear fusion is a self-sustaining reaction, and that's why we have stars that have incredibly long lives, because they're just burning their own fuels again and again and again, and it just keeps on going, kind of this cyclical process. And that's because you've got this tendency to release more energy than is needed to bring the two particles together, which means they can keep cycling through a process of fusing and separating, because the energy is released, and then it brings two together, and then it forces two apart, and then it brings two together, and so on, because all these things, of course, are having these interactions while surrounded by lots and lots of other atoms that are having similar reactions. So it's just a continual process of things being forced into each other and then forced back apart. And this is why actually fusion is such a fascinating thing to us here on Earth, because we don't really see it here. We see it out in the stars, and so it's kind of this kind of almost mythical thing that we want to be able to create here on Earth and harness in some way. Now, when the fusing nuclei have masses that are higher than that of iron, the fusion process is generally going to require the absorption of energy, and this means that it's endothermic. And this means that fusion is generally only found in these lighter elements because it's very rare for you to actually have enough energy to create fusion in these higher mass atoms. So things like iron and above, you generally have to have so much energy that you just aren't going to see this happening here on Earth. You might see it out in space somewhere in stars that are incredibly hot and have all this stuff going on, but certainly not here on Earth. Actually, one of the places that you see this most often is when you've got supernovas that are occurring. So these incredibly intense astrophysical events, not just, kind of on a daily basis, a star, but on when you've gotten a star to a certain point where everything is really exploding in the most intense way possible. That's when you've got the fusion of heavier nuclei, which leads to something that we call nucleosynthesis, which is the creation of these nuclei of the heaviest elements that we find in the universe. So that's nuclear fusion. So what's nuclear fission? Well, it's the splitting of a nucleus into smaller and obviously lighter constituent parts. And this can result from either a nuclear reaction or from radioactive decay. So I'll take each one of these in turn. A nuclear reaction is a process in which two nuclei, or a nucleus and an extranuclear subatomic particle, when these things collide with each other and produce one or more nuclides. And a nuclide is an atomic species that's characterized by the constitution of its nucleus. So whether it's got protons and neutrons in a particular nuclear energy state. So in other words, basically what we're describing here is when you've got one nuclide transforming into another during a nuclear reaction. And if an interaction occurs and neither particle undergoes a permanent change, then we just call this nuclear scattering. And obviously there's nothing really exciting happening in terms of energy being released. But when you do have these things actually impacting each other and making a difference on each other, that's when you've got a nuclear reaction. So the other process that we can have causing nuclear fission is radioactive decay. And this is a process in which the nucleus of an unstable atom loses energy by emitting particles of ionizing radiation. And these are alpha or beta, this is really hard to say for me, alpha or beta particles or gamma rays. So what do I mean specifically when I say ionizing radiation? Well, this is particles that carry enough kinetic energy, so energy associated with their motion, that they can liberate an electron from an atom or from a molecule, thus ionizing it. And that leaves it with a different charge, and therefore leaves it in this state when it can react. It's interested in, and it's more likely to react with the other molecules around it. So, as I said, there are three different types of ionizing radiation. Alpha particles, which are 2 protons plus 2 neutrons, which we also recognize as the helium nucleus. Beta particles, also known as beta rays, these are high-speed electrons or positrons, and positrons are known as anti-electrons and are the anti-particle or antimatter counterpart of electrons. And this is a concept that I've always found to be kind of bizarre, that you can have something, but you can also have the anti-something, and then these two things can react with each other and basically just cause annihilation. And in the case of positrons, when positrons and electrons come together, this collision leads to annihilation, as I said, and the production of 2 or more gamma ray photons, which is, again, the third type of ionizing radiation. And these are extremely high-frequency electromagnetic things that cause radiation, and each photon has extremely high energy. These tend to be produced by decay from really high energy states of atomic nuclei, and they're produced after the nucleus emits an alpha or beta particle, which then leaves the nucleus in a really excited state. So the nucleus lets go of this 2 protons plus 2 neutrons, or it lets go of a high-speed electron or positron, and then that means that it's kind of unstable because those things were keeping it in that stable condition in kind of a lower energy state. And once those are gone, then all of a sudden it needs something to happen in order to release that energy, because that just means it, it's incomplete. It wants to react with something. It needs to get rid of that instability. And so that's what happens when you've got these gamma ray photons being produced, because that is a way to kind of alleviate all of this tension in a sense. And this is one of the things that can happen when you've got electrons moving between shells. So what does all of this stuff mean in the real world? I'm describing these terms and these interactions that sound really exciting, and they sound like they might happen somewhere off in the universe, but do they really have any kind of application to the real world? Well, nuclear fission is what drives nuclear power plants and also nuclear weapons. And one of the things that I thought was really interesting about the story of Lise Meitner was that she, as soon as she realized what nuclear fission was and how it was happening, she realized that it could have a horrible potential to unleash a lot of energy in a really negative way. She knew that it could be weaponized, and she absolutely refused to have anything to do with the building of the bomb. However, of course, her contemporaries, many of them were interested in creating this weaponry because they were hoping that it might bring an end to World War II. And so this is when people were really pursuing, almost immediately off the back of the discovery of fission, people were interested in figuring out how you could make a bomb using this technology. And now, of course, we do use it in a much more pleasant way, which is to, pleasant to some, I suppose, which is to create power and electricity and energy for the rest of us to use. Now, of course, some of that tends to be a bit dangerous, as we saw with Fukushima. There can be some leaking of the results of this, and we don't yet really have it nailed down to make it as safe as it can be. But certainly it is very attractive because you can have this, this kind of fundamental physical process leading to all of this energy, and that certainly does seem to be an attractive option rather than using things like coal and oil. Even more attractive is the idea of having controlled fusion. And it's something that actually has been possible for decades, but not really at commercial scales. So there have been these little devices, well, relatively little, that scientists have created so that they can conduct controlled fusion in laboratory settings and study the effects, study the process, see what happens when all this is happening. And this is one of the big things that people are really hoping we can ultimately use in order to have an alternative source of energy. So even better than nuclear fission is this idea of fusion, because potentially it's something that could be a bit cleaner and possibly a bit safer if they can figure out how to do it. So they are really hoping that they can harness this power and use it as an alternative to fossil fuel and also to nuclear power. But of course, this is at least several decades away, maybe even a century away, depending on how much money and how many resources are put into this kind of technology. But all of this is made possible by all of these discoveries that started centuries ago and then really accelerated at the turn of the last century in particular, so in the early 1900s. And it's really fascinating to see that all of this work in chemistry and in physics is now suddenly having a huge impact on kind of our daily lives in terms of what energy we're using and the products that we have in our homes, our electronics, things like that. And all of this is actually quite a timely topic, given that there is now this excitement and this interest kind of building in terms of physics and astrophysics especially. So last night in the US, this show called Cosmos debuted with Neil deGrasse Tyson, who is, of course, this really famous astrophysicist now on Twitter and famous in the US and now a little bit abroad. So I think people are becoming kind of more and more intrigued by what is physics and how does it impact us and what can we learn from studying it. So hopefully, if you are one of those people who's kind of been interested in this concept for a while and watching its growth on the public stage, you will have found today useful. Maybe you know a little bit more about the atom than you did before. Maybe you know a lot more terminology, even if you can't remember it. I know that I certainly won't, but maybe now you know what a hadron is and a baryon and all those exciting things. And if I did make any mistakes, if you are a physics expert and you found some flaws in what I was talking about, please let me know so that I can update this all on the website. I did just do all this reading for myself to become a bit more educated, and I'm certainly not an expert in physics, so I'm happy to have you set me in the right direction. But that is all from me for right now, and I will leave you with Massive Attack singing our last atomic anthem of the day, and that is Splitting the Atom.